All right, so we're getting into aqueous equilibria here. And again, this is going to be generalized equilibria was the first one we did, right? And that was 15. And then we did acid bases, and we're more specific types of equilibria, right? And that was 16. And now we're getting even more specific and more conditions going on. And what that means is every time you learn more about this, there's less math work you have to do. Okay? So mathematically, these problems are going to start getting really easy. But you have to understand the concepts, you have to understand the terminology to set them up. Okay? And so they're kind of more of a, can you read the problem? Okay? Do you understand the language? All right, now, so the importance of buffers, that's for what regulates the pH of your organisms. These are buffers. So for example, the CO2 that you're breathing out right now, that CO2 is actually primarily in the form of carbonic acid in your blood. Okay? That's actually how you transport the CO2 in your blood. It doesn't bind hemoglobin like most people think. And so what you're actually looking at in your blood is mostly a carbonic acid buffer system. And that's why you're actually quite resistant to pH change. Okay? The solution pH is going to be controlled by the presence of one or more buffer solutions, typically in something like an organism or in a buffer system that we're using to, like in your drinks, by the way. They have buffer systems. Your soaps, shampoos, all those have buffer systems. The buffer solution is going to resist change in pH by neutralizing the added acid or the base that you add. And again, this is going to primarily be done through the common ion effect, which we'll define right here. So this right here is the common ion effect. So in your aqueous solution, for example, we have nitrous acid, HNO2. This is a weak acid, and so it's going to be in equilibrium with the nitrate anion and the hydronium right there. Now, if we add a strong electrolyte, like sodium NO2, then what is going to happen? Well, this will break completely apart, right? And it will give us that ion right there. What happens to an equilibrium when we add a bunch of product? It shifts towards the left, okay? And so make sure that you remember your Le Chatelet principle, shift left, shift right. So if we add a bunch of NO2 minus, we're going to shift this towards the weak acid, aren't we? What does that mean? Well, it means it ionizes less, doesn't it? Okay? And we end up with more of the weak acid there. Now, the same thing can happen through, say, hydronium. So if we added more acid to this, it would increase the hydronium, wouldn't it? That would shift it towards the left, meaning we would consume some of that hydronium, wouldn't we? Okay? Meaning it would resist pH change, right? And so it's a lot like a tilted table or a shock. You ever seen a spring shock work? It's a little spring like this, pointing downwards. And when you hit it, it resists that force and then pushes back out against it. Okay? We're seeing the same thing here. So what would happen if you added, say, OH minus to this, by the way? Like a base. Well, the base would react with the H plus in the solution, wouldn't it? And that means the H plus would go down and the equilibrium would shift which direction? Shift right. Making more H plus, right? And so it's going to fight the H plus going down. And that's why that's called a buffer. So the suppression of the ionization of your weak electrolyte when combined with strong electrolyte containing a common ion, this is actually the definition, the textbook definition of common ion effect. So literally a common ion and the effect it has on that equilibrium. Okay? So let's calculate the pH, A, of an aqueous solution containing 0.3 molarity HNO2, and then B, a solution containing 0.3 molarity of HNO2, and then 0.2 molarity of NaNO2. The Ka of that weak acid is 5.6 times 10 to the negative 4. Now, you'll notice really quick, like, that last chapter, I actually kind of already did this to you, didn't I? I already made you do a problem like this. But you didn't really understand why it was happening, did you? Now, we're exploring why is that happening, okay? So the first problem is just a normalized problem, right? So we just write out our equilibrium for a weak acid, HNO2 plus water yields H3O plus NO2 minus. Cool. And then the next thing what we have to do is we go ahead and put our initial conditions. We have 0.3 here, 0 and 0. And then it's minus x plus x plus x. And we get 0.3 minus x, and x. And so we want to figure out pH. So we plug these in to our equilibrium expression, our Ka expression here. And that's going to give us x times x over 0.3 minus x. Now, when you see something like this and the Ka is a 5.6 times 10 to the negative 4, you can probably ignore that minus x down here, right? So we're going to go ahead and do that. We're going to say that bottom part is just 0.3 now. And we're going to multiply that over and take the square root of that. Okay. Did I lose anybody in that chain? You've done it way too many times by now, haven't you? Yeah. Luckily, we're on the third ice problems chapter, equilibrium chapter. And so this is the last chapter you have to do this. Okay? We'll get to take a break from this in a bit. So we go ahead and figure out that number, which is 0.013 molarity. That's X, but X is also the H3O plus, isn't it? And so that's our concentration of H plus. So we need to double check two things. First off, we did not want the H plus concentration, we want pH. We're going to have to do that. But we also need to double check that we fulfilled the 5% rule. This one was actually pretty close, wasn't it? So we got a 0.03 for our X, 0.013, for our X. We had 0.3 for the number is subtracting from. And so we take that times 100% and we get 4.3%. That is below 5%, but just barely below 5%, isn't it? Yeah. So we came pretty dang close. All right, so the next thing we're going to do here is we're going to take pH equals negative log of our H plus concentration, which is that 0.013. We're going to do that on our calculator. We'll get a pH of 1.89. And that makes sense. We add an acid, didn't we? Okay. And so that's part A. Fantastic. The next problem we have is, well, we have a similar setup, don't we? 0.3 molarity. We have the same Ka, but now we're adding this right here, aren't we? Okay, and so sodium right here, that's the cation of a strong base, isn't it? And then this right here, this is the conjugate base of a weak acid, this weak acid, in fact, right? Okay. And so this right here, that's a base. We're going to be adding that base, aren't we? And that means that we're adding 0.2 molarities of that directly at the beginning, aren't we? So that's our initial value. So we take our ice table, and we have 0.3 here, same as before. This is still 0, but this number is not 0, is it? No, we start with that right there. And so we start with 0.2 of that. So we're going to go ahead and go minus y plus y plus y so we can differentiate it from the x's and we don't get confused when we look at our notes. Okay? And then we're going to take 0.3 minus y. This is y here. This one's 0.2 plus y, isn't it? Okay. And so we plug that into our Ka expression that we already generated before. And that's going to give us y times 0.2 plus y divided by 0.3 minus y. Okay, so this right here, this y value, that x before was already pretty small, wasn't it? we're adding some of this. This is going to push this reaction even further this way, isn't it? By the Chatelier's principle. If we add on this side, we push it towards the reactants, don't we? So that's going to make this number here even smaller. So we're probably okay if we make that assumption. Okay? And so the plus y here, let's get rid of it. The minus y here, we're going to get rid of that. Because we can assume those are so small, they're not going to matter. And so that's going to be equal to the 5.6 times 10 to the negative 4. Now notice that that actually made our math even easier, didn't it? So we multiply over 0.3, we divide by 0.2, ta-da, we'll get our value of y. Our value of y is 0.00084, that's even smaller than before, so that should be within the 5%, shouldn't it? Okay. I'm going to go ahead and give you the double check, just in case. By the way, do you have to actually do it for both numbers? Nah, you can just do it for the smaller number, right? So 0.00084 divided by 0.2 times 100%, that gives you that right there. Obviously not going to be greater than 5%, right? Because we're even smaller. The previous one was less than 5%. Okay, so we're again going to calculate our pH. And so we take the negative log of that value. So negative log of 0.00084, that gives us a pH of 3.08. So, a solution, your book defines a buffer solution as a solution containing both a weak acid and its conjugate base. And that is called a buffer solution. Okay? It's not wrong. Kind of a weird definition, way of defining it, but it's not wrong. Another way of defining it, it's a combination of an acid and its conjugate base, or a base and its conjugate acid, right? They have to be weak acids, weak bases. If you had a strong acid, what would happen? You'd have none of one side, right? So strong acids, strong bases, they're never going to establish a buffer solution. Because strong acids, strong bases, completely ionize. They don't have an equilibrium, do they? And remember that buffers are going to be an equilibrium that you're going to push on. Okay? Like a shock absorber or a bouncy mattress. Right? Is the bouncy mattress a better example? Okay, we'll use bouncy mattress. Okay. And so again, this is going to resist pH change. When an appreciable quantity of an acid or base is added, strong acids or bases are much easier to calculate, and so those are typically what you're going to see in this class. Okay? If you wanted more complex problems, you'd have to join me in something like an analytical chemistry. Okay? A buffer has significant quantities of both the HA and its conjugate base. This allows it to shift in either direction when either acid or base is added. How well would a mattress that's like super thin work? Is it very bouncy? No, it's not very bouncy, is it? How well would it work if you put like a huge heavy board on it? Wouldn't be very bouncy either, would it? No. And that's because if you compress this to be very thin, to not have a lot of concentration it can go through, then it's not going to work well to resist pH changes, is it? Okay? It's the same thing. So, how a buffer works. This is a nice little graphical demonstration, though keep in mind that these are not actually necessarily equal concentrations, okay? But yeah, you want them to be as equal as possible. So you have the most you can consume, right? Okay, in either direction. Now, right here we see if we add base, what's going to happen? Well, we're going to consume some of the acid. That will resist that pH change because it will consume the base, won't it? And then that will give us more of the conjugate base, less of the weak acid. Okay? Now remember, which exactly of these is our conjugate? Doesn't actually matter, does it? If we have a weak base, it'd be the conjugate acid, right? But the conjugate acid of a weak base is a weak acid. Okay? A weak acid, conjugate base, Well, the conjugate base for a weak acid is a weak base, isn't it? So it doesn't actually matter here. Conjugate is just a artifact of us deciding one direction versus the other, right? Okay, and so here, again, we add an acid. What's going to happen? We're going to consume some of our base here, our weak base, and that's going to give us more of that conjugate acid. Okay? So let's determine which of the following combinations of species will result in a buffer solution. So here we have HCl and NaOH. Okay, so what you want to look for is weak acids, weak bases that have a common ion effect, right? And so, are these weak acids or bases here? No, that's a strong acid, one of the 7 strong acids. In fact, it's the stereotypical one. And then this is the stereotypical strong base. And again, the strong base is group 1, lower group 2, right? With an OH. This right here, HCO3 minus and CO3 minus. What do those have in common? Yeah, they're both CO3, aren't they? And then, what's the difference between them? An H and a plus, isn't it? Yeah. So this is actually a acid in its conjugate base, isn't it? Or a base in its conjugate acid. It's true. Either way you want to look at it. And so right here we have a weak acid-base pair, don't we? That have an ion that's in common. Okay? Which is the CO3. Okay, so this is a buffer solution right here. HBr and NABr. What do you think? Is this a buffer? Does that make a buffer solution? So is this a weak acid? HBr, that's one of the 7 strong acids, yeah. So that's one of the 7 strong acids. This right here, on the other hand, is the cation and anion for a strong base, strong acid right there. Okay. And so this is not going to make a buffer solution, even though it has a common ion effect, because this has no basicity to it. Okay? It's a strong acid, strong base pair sort of thing. Okay. By the way, anybody know what this would give me if I reacted those? Uh-huh. So OH minus and H plus, that would give me water. Na plus and Cl minus, that gives me salt. Yeah. This is just table salt when you react them in equal amounts. Yeah. Table salt water. I know. I made salt water. Ooh. Okay, so let's explain how a weak base, B, and its conjugate acid, BH plus, form a buffer solution. So how in the heck do those work to form a buffer solution? Well, your B and BH plus, they're going to have an equilibrium, right? So B, reacting with water, is going to give you BH plus and OH minus, right? And this is an equilibrium. So when you push on this equilibrium by adding H plus or OH minus, by adding an acid or a base, then what's going to happen? Well, if we add OH minus, we're just going to shift over here to the base, aren't we? If we add H plus, this is just going to get rid of the OH minus, and this is going to shift over to the reactants, isn't it? And that's going to end up resisting our pH changes every time. Just like a springy mattress resists your pH change, or your change in distance, when you push on it, right? And then forces you the other way. Okay, so let's calculate the pH of a buffer containing the initial concentrations of NH3, concentration 0.21 molarity, and NH4 plus, the concentration there of 0.14 molarity. Now, the Kb of NH3 is going to be this value right here, 1.8 times 10 to the negative 5. Okay, so the first step of these reactions is to figure out what equilibrium you're working on. Okay? And the easy way to do that is that equilibrium has to have both species in it, doesn't it? Okay? So we're going to be going from NH3 here to NH4 plus. This gave us a hint that Kb was probably the one we kind of wanted to work on. Okay? The other hint here was that this is a base and not very good acid, right? Okay? Very poor acid, in fact. The other hint being that this is a larger amount as well. So if we go ahead and write that out, we get NH3 plus water. This goes to NH4 plus OH minus. Okay. And again, this is a much better base than this is an acid, right? So this is going to end up going in this direction either way. All right, so we go ahead and put our initial values in here. We're large enough numbers that we can go ahead and assume OH minus is 0. This is again going to be the 0.21 minus x, 0.14 plus x, and then we're going to get x for the OH minus. We write out our Kb expression. This is going to get substituted in with our equilibrium numbers here. And so we get 0.14 plus x times x on the top. On the bottom, we get 0.21 minus x. Anybody get confused at all going to there? Everybody feels like a well-oiled machine going there? Okay, well then, more homework. More homework. By the end of the homeworks, if you do all those, you're going to be a very well-oiled machine. Okay. Now, again, because this is a pretty big value, this one's not a very big value, right? And you may have been noticing, because we're putting in numbers here, these numbers of x become really small, don't they? Yeah. And so we're actually going to end up basically always being able to put the initial value in for the equilibrium. Yeah. We'll prove that a bit more in a bit. So we get 1.8 times 10 to the negative 5. Again, this is going to be 0.14 here. We can get rid of the plus x. The minus x we can go ahead and assume we don't need to do. It's not important. It's not a large enough value to affect our results. 0.14 over 0.21, and that's times x. Now, notice, by the way, that you could actually solve this down right here if you'd like. You could go 0.14 divided by 0.21, and then you could divide that number over. Okay? I just do it this way because it's easier to do that way with one step and then not have people get confused. Right? So times 0.21 divided by 0.14, and that gives you this value right here. And that is going to be 2.7 times 10 to the negative 5 molarity for your OH minus concentration. Now, there's a few things we still need to do, isn't there? We wanted pH. That's the answer to the problem, right? The other problem is that we assumed something, didn't we? And Dr. Clausen tells me if I assume something, what? Well, if I don't check it, it's going to make an ass out of you and me, right? Okay? And so I need to come down here and I need to check, is that less than 5%? Okay? And so I'm going to take that 2.7 times 10 to the negative 4. I only have to do it for the smaller number, actually. So divide by 0.14 times 100, and that gives me well less than 5%, right? Totally fine. Okay, good assumption. So to get the pH, the easy way to do that is to take 14 minus the negative log of your OH minus concentration. So I'm going to go 14 minus the negative log of 2.7 times 10 to the negative 5. When I solve that out, that gives me 9.43. Anybody have any questions? Does it make sense to be over pH 7? Yeah. I added a base, didn't I? So let's calculate the pH of the same system, treating the initial concentrations as equilibrium concentrations. So again, we're going to go ahead and do the NH3 plus water yields NH4 plus OH minus. We actually already kind of did this, and we did this by assuming we could get rid of the plus X minus X, right? So we're just going to straight up skip the entire idea that we need to do an ice table, okay? And we're going to go, our equilibrium conditions in these buffer systems, they're always just going to end up being those initial concentrations. Hell with all that extra work. And so we're going to substitute those initial concentrations in, 0.14 and 0.21, and then that's X there. We go ahead and solve, so times 0.21 divided by 0.14, you're seeing that this is actually the exact same thing we ended up doing, isn't it? Okay? And we do the exact same work as we did before, and we get 9.43. Okay? And what does that tell you? That tells you in almost every case you're working in a buffer solution, because you have initial concentrations on both sides, the amount of X you're going to make is tiny. Okay? You basically almost never need to deal with the plus X minus X, and you can just skip all those steps. Right? And so there's actually a way that in buffer systems we can skip the ice table. We have the Henderson-Hasselbalch equation. We're going to go ahead and derive this real quick so that you can use this. So right here, this is the equilibrium for a weak acid. And this right here is the Ka expression, like we normally would have done. So if we go ahead and rearrange that Ka expression so that we can get the H plus on one side, because let's be honest, that's what we're usually solving for, right? Yeah, pH, which is a form of H plus, right? So we're going to go ahead and get that on one side. Everything else ends up on the other side. Does anybody have any questions about how I get that? Losing anybody? Okay, so again, this is just restated. Now, I usually don't work in H plus concentrations, do I? I usually work in pH, right? So how do I get into pH again? Well, I just take the negative log, don't I? So I'm going to take the negative log of both sides, negative log of H plus, negative log Ka, negative log of HA over A minus. I went ahead and left that ratio together. Is everybody okay with why this could get split up like that? So if I took the log of this whole thing, this multiplication, when I split the logs, turns into addition of the two logs, right? So if you note the negative log of the H plus concentration, that's just pH, isn't it? The negative log of the Ka, well, that's just pKa. And the negative log of this other one, well, that's a ratio that has some sort of meaning, doesn't it? And so I have to keep that. Negative log of HA over A minus. Note that's the weak acid and its conjugate base, or the weak base and its conjugate acid. Okay, so this is the sort of the starting here, but this minus log causes a lot of people to have troubles, and typically they want the fraction that would end up resulting. You wouldn't want to have the fraction that stays together, okay? Most people want the end result, right? So what we're going to do here is we're going to go ahead and make that negative log here a plus log. And that's the correct form of the Henderson-Hasselbalch equation. This is actually the work you need to do to prove that when you change the sign right here, it flips the internals. Okay? Is everybody okay with that if you take the negative of the negative log, that's going to flip the stuff inside? Or would you like to see the proof? Yeah? You good? Okay. Okay. Yeah. So if you change the sign of a log, it just flips everything inside, right? Okay. This is actually doing it the long way and proving it, in case you're curious. Again, this is actually the proper Henderson-Hasselbalch equation. I'm going to be honest with you, everybody that uses this quite a bit over time forgets which way it goes. Because it actually doesn't matter, right? Like, that's a really easy thing to do. Oh, I put my weak acid over my weak base. Okay, it's a negative here. Oh, I did it the other way? Okay, I'm going to put a positive there. And you just flip signs, right? You'll catch me doing that quite a bit. What's my time, by the way? 10? Oh, okay. The pH equals pKa plus log of the base divided by the acid. That right there, Henderson-Hasselbalch formula equation, it can be used anytime you have a buffer system where your initial concentrations are significant. Okay? Now, you're going to notice something about this equation here. This right here is molarity. This is also molarity. The units inside of here are unitless because they're going to cancel, aren't they? And so normally molarity is moles over volume, right? But these are in the same solution, aren't they? So what happens if you have a 1 liter solution over a 1 liter solution? They cancel, don't they? 100 liter solution over 100 liter solution. They cancel, yeah. Yeah, so it doesn't matter, does it? So you can actually directly just put in moles here. That's fine, okay? In fact, you can use most units of concentration and moles because they'll cancel, and they're the same solution, okay? The big important part of this has to be the same units. What happens if you put moles in one place and molarity in the other? Doesn't cancel, right? Damn it. Yeah, I mean, it's an easy mistake to make. Very common mistake to make. It's why I do that like wherever I'm working with you and talking to you guys. I'll be like, express your units. Write your units. Yeah. So let's calculate the pH of the formic acid buffer with the following concentrations. The Ka of the formic acid is 1.8 times 10 to the negative 4. And so what we're going to find out here is I just made a big shortcut for you, didn't I? By giving you that Henderson-Hasselbalch. So again, we have a buffer solution, right? And it has significant concentrations. And so we're going to go ahead and plug those in to the Henderson-Hasselbalch. So we take our Henderson-Hasselbalch, pH equals pKa plus log of base over acid. We plug in the Ka here, which is negative log of this value, 1.8 times 10 to the negative 4. Then it's going to be plus the log. Again, we take the base. The base's concentration is that sodium formate concentration, isn't it? Okay? And that's 0.12. This is going to be divided by the acid, 0.17. We go ahead and solve that. So the log of 0.12 over 0.17, that's negative 0.151. The pKa from that Ka is 3.74. We add those two things together, that gives us 3.59. Now what you're going to notice here pretty quickly, if you have more base than acid, you're going to get something that's pH is higher, right, than the pKa. If you have more acid than you have base, you're going to get something where the pH is lower. Exactly. And so this makes sense. We're lower than the pKa, aren't we? Yeah. Okay, and so right here we have again the pH. We get that same 3.74 number, but in this case we have 0.150 moles of the sodium formate and 0.1 moles of the formic acid. Do I have to do anything to those moles? Oh, they're the same solution, right? So whatever the volume is, it doesn't matter. Okay, I can just ignore that. So I'm going to take 0.15 divided by 0.1. I'm going to take the log of that. And then that's going to be plus that 3.74 that I got for the pKa. Notice that this value is higher because now we have more base than acid, right? And so we get 3.92 for our pH. Isn't that nice? Things are getting pretty easy mathematically, aren't they? A lot less work. Okay, By the way, if anybody's planning on going med school and stuff, very popular med school problems. Okay? And you'll have to kind of learn to do those in your head. Okay, so we'll go over it in biochem though. So when the A minus is greater than the HA, or when you have more base than you have acid, that means the pH is going to be higher than the pKa. When the acid is greater than the base, then that's going to mean that the pH will be lower than the pKa. Makes a lot of sense. Yeah, it's the normal directions for pHs, isn't it? When they're equal, guess what's going to happen? Anybody know what the log of 1 is? Okay, if I take 10 to what power would I get 1? Yeah, 0, exactly. And so 0, yeah. And when these two terms are equal, that gives us this value is 0. And so pH just equals pKa, period, you're done. Okay? So let's calculate the relative concentrations of acetate ion and acetic acid that must be used to make a buffer solution with a pH of 4. The Ka of acetic acid is 1.8 times 10 to the negative 5. Okay, so we're going to go ahead and start plugging this puppy in. Now we have a Ka, we have acetic acid. We want a ratio, don't we? Hey, what was in the Henderson-Hasselbalch? Was that a ratio? So we're going to take that Henderson-Hasselbalch, we go ahead and rearrange it. So our log of our ratio equals the pH minus the pKa. We plug in our pH of 4 that was given to us. Our Ka was given to us, so we need to take the negative log of that. So negative log of 1.8 times 10 to the negative 5. And that's going to give us our ratio, the log of our ratio, which is negative 0.74. Now the next thing we have to do here is we need to get rid of the log, don't we? We don't want the log. So we do that by taking 10 to the power of both sides. So 10 to the power of 0.74, that's going to give us 0.18. And that's our ratio, isn't it? What does that effectively mean? Well, if we have 1 HA, that would give us 0.18 of these, wouldn't it? Okay? Or another way of saying that is we had 100 HAs, that would give us 18 of the A minuses. Buffer capacity. So this is the effectiveness of a buffer solution. This can be based on two factors. You have your buffer capacity and your effective pH range. The buffer capacity is actually going to refer to the ability of the buffer solution to resist a change in pH when an acid or base is added. So the buffer capacity is dependent on the concentration of HA and A minus. Anybody ever used those big trampolines? No? Okay, how about mattresses? Did anybody jump on a small mattress and then jump on their parents' really big mattress? Damn it, you're supposed to do it in secret when the parents are gone. Okay, you understand the concept though that a larger spring is going to give you more resistance, right? So if we have more capacity, larger concentrations, we have more of the acid or base that we can resist, don't we? Okay? If we have a very small one, then we're going to end up running it out. Okay, let's use the TikTok example I used last time. I thought the mattress example would be better, but apparently not. Okay, we're trying to do the new TikTok dance. Should we do it on top of the peak of a tower? It's only about a foot long. No, why is that? Your margin of error is 0, right? Yeah. How about the Bethel's roof? Nice flat, lots of space. That can work out? That'd be better, yeah. I mean, you shouldn't fall through it. We had a whole team up there working on it 3 times. No, they did not. They really did not. But you get the idea, right? Yeah. Lots of room for error. And again, that's that capacity, right? Capacity for error in that case. This would be buffer capacity. Okay? Okay, so buffers are going to be most effective when they're within 1 pH unit of your pKa value, because that tells you how much of the room you have left. Okay, so again, the buffer's pH range is pKa plus or minus 1. And that's kind of like the roof example again. Yeah, Bethel's roof is quite safe if you dance in the middle of it, right? But if you dance on the edge of it, not so safe anymore, right? And again, that would be that same thing. Once you get, to plus or minus 2 pH units from there, you're running out of so much room that you're dancing on the edge. You're very likely to go over. Okay. All right, so we're going to use table 16.2 to select some weak acid or acids that can be used to buffer a solution at 5.5. So if we want to be a pH of 5.5, what should our pKa be? Okay, remember our pH range should be plus or minus 1. Yeah, this is easier to do with pKa's, by the way. It's a hell of a lot harder with Ka's. Okay. So what you want to do is you want to look at your Ka's or pKa's specifically, and you want to go ahead and find something that's plus or minus 1 of that. Okay. Now I'm going to go ahead and do it so we get in the Ka's, because that table happens to have Ka's. Okay. But you can actually do it two ways. You could convert the table to pKa's, which if you're using Excel or something is way easier. Okay? Or you can take your plus or minus 1, so we have a 5.5 pH we want. Plus and minus 1 is going to be 4 and 6, right? 4.5, 6.5. And so what we're going to go ahead and do is we're going to round that. So what we want is a 10 to the negative 6.5, a 10 to the negative 4.5. A Ka within that range is going to work nicely. Okay? Okay, so we got these values. They're 10 to the negative 5, 10 to the negative 7 here, and then times 3.16, right? Which is that 0.5. This right here, we're going to look at that table, and acetic acid falls within that. Okay? And so acetic acid is going to be okay. It's the only one on the table that's actually close. And so our acetic acid will be what we'll want to make this buffer out of. Okay? Which is actually pretty convenient because that's basically vinegar. Yeah. So let's calculate the pH of the following solutions. We have a buffer that contains 0.150 moles of acetic acid and 0.195 moles of sodium acetate. And so this is going to be in 1 liter, though that doesn't really matter, does it? Okay. So what type of problem is that? Henderson-Hasselbalch, isn't it? We have a buffer. It has a decent concentration. It's not super dilute, right? Okay, we can work with that. Now, one of the things I want to keep in mind here is that, let's say I forgot the Henderson-Hasselbalch formula. I can't figure out how the fuck to use that. Oh my God, what am I going to do? Can I calculate this as an ice problem? Oh yeah. Yeah, I can calculate this as an ice problem, can't I? Okay. The Henderson-Hasselbalch formula is just a time-saving technique. That's it. That's why I was like, ice problem, right? So you can set up an ice table, Ka expression, equilibrium expression. You're going to be good for these 3 chapters, right? That's all you actually need to know. Okay? It's just going to take you extra time. Okay, so we go ahead into the Henderson-Hasselbalch here. pH equals pKa plus the log of the base over the acid. Our base is which one? You got it. Yep, sodium acetate. And the easy way to figure that out every time is look for which one that doesn't have an H+, right? Yeah. This has an extra H+. There you go. That's your acid. This one's your base. Okay, so I substitute that 0.195. That goes in the top here. and I'm going to divide that by the 0.150. I'll take the log of that, and that gives me that term right there. I'm going to take the negative log of my Ka. My Ka is that same Ka I just looked up for acetic acid, isn't it? And so I'm going to plug that value in. And then this is going to be this plus this, and that will give me 4.85. By the way, you can actually ballpark the figures pretty well if you're doing multiple choice by just looking at that pKa and seeing how far off this is. If these are fairly close, not 10 times numbers, then this is pretty close to your answer. Okay? Anyways, we get a pH of 4.85. That makes a lot of sense because we have a bit of extra base, don't we? Okay. Anybody have any questions on how to get that? Okay. Yeah, they're honestly, once you do that a few times on your own, it's going to be pretty simple. You'll be really used to it. So after 0.03 moles of solid NaOH is added to the buffer from part A with no change in volume. Okay, so what we need to do here is we need to go ahead and react away some of our acid, don't we? Because NaOH is a strong base. And so we're going to have that 0.03 moles of NaOH that gets added. Well, the acid and NaOH, that's a 1-to-1 ratio for the reaction, isn't it? Yeah. Each OH minus is going to react with one H plus to form water, right? Okay, now you'll notice that that is going to form additional sodium acetate, isn't it? Which is our base. Okay, the sodium's not actually the important part, by the way. The acetate is the important part. So even if this was potassium hydroxide or whatever, it doesn't matter, it would still form the acetate. Okay? So here we have 0.150, that's what we started with in that A. This is going to be minus this number here, which is the 0.03, and that's going to give us 0.12, right? That number gets added onto the acetate. So 0.195 plus that 0.03, that gives us 0.225. Notice this is actually just straight up stoichiometry, isn't it? Yeah. Of course, all of our base has to be consumed. It's always good to make sure and double check that, okay? And so all of our NaOH is consumed. Anybody have any questions on that so far? Okay. We're just setting up a problem here. We're doing what do we have, what do we need, how do we get there, aren't we? So now we just have to take our Henderson-Hasselbalch, we have to plug in our new moles for these numbers. Again, because the volume doesn't change and we didn't have any weird stuff happening with the volumes, we don't actually care about the volume at all, do we? Yeah, we can just do moles. So we plug in 0.225 divided by 0.120, take the log of that. If you were smart on a series of problems like this, you would have went ahead and written down your pKa number because you'd needed it multiple times, right? Instead of just doing the whole thing in your calculator. And so this would be the negative log of that Ka again, giving us our pKa. When we add those together, this gives us 5.02. Note that that was, again, a very small rise because we added more base, right? And so, again, that answer makes sense. We got a little bit more basic, okay? But almost nothing, right? Hell of a lot less than if we had just straight up added it. And so it resisted some pH change. Nice buffer. So after the 0.03 moles of solid NaOH is added to 1 liter of pure water, so we're going to add that sodium hydroxide to pure water now. No buffer. And so what we have to do here is we have to figure out the concentration of 0.03 moles of sodium hydroxide when we have a 1 liter solution. And so we need to get the pH here. To get the pH, we take the pH equals 14 minus the negative log of this concentration, right? This concentration being 0.3 divided by 1. So, and that's going to give us a pH of 12.49 units. Okay? That was a hell of a lot more basic, wasn't it? Yeah. So that's, without that buffer, we would have risen a lot more in pH, wouldn't we? See that? The buffer really did its work. Remember, those pH units, that's a 10 to the negative 6. That's a million times difference in acidity and basicity, right? Okay. All right. All right, so next thing we're going to do is we're going to talk about titrations. So in a titration, a chemical reaction is carried out by mixing two solutions in the presence of an indicator. So a solution of known concentration, this is called the titrant, is added to a solution of unknown concentration. This is called the analyte. It's the one we're analyzing. Okay? Titrant, known, it's the measuring stick we're going to measure with. The analyte, unknown, what we're trying to measure. The indicator is going to determine the stoichiometric equivalence point of your titration. Now, notice that this is a very special way of using indicator. We're using it as, hey, these line up. Okay? It's indicating that, hey, we have put in an equal amount of base to our acid, or an equal amount of acid to our base, right? And so those have an equal stoichiometric equivalence or an equal stoichiometric amount, i.e. the reaction has gone to completion. So the volume of the titrant at the equivalence point is going to determine the moles of the titrant and is going to allow for the calculation of your concentration of your analyte solution. So this is actually a video of titration with an indicator. Does this look somewhat familiar? Mm-hmm. Yeah, you should have done this in lab. Mm-hmm. It's a pretty simple...
Sodium hydroxide solution of known molarity is added from the burette to the Erlenmeyer flask.
You don't actually have to do this known one in the burette. You can do either one. It doesn't actually matter. Okay?
Containing an exact amount of a hydrochloric acid solution of unknown molarity. The sodium hydroxide is added rapidly at first, and then slowly as the reaction nears completion.
Add together. So that's very...
An indicator added to the hydrochloric acid solution is used to determine when the reaction is complete.
You see the flaring? Okay. Flaring is going to happen because as you hit droplets in here, you'll have a local concentration that's higher. This tells you that you're getting close to the end, but you're not at the end, okay? It's not saturated.
And the endpoint has been reached because it's colorless in the hydrochloric acid.
So see how it's flaring here? Okay, so it's becoming more basic at these points. These points are still acidic because it takes time to mix. And this is phenolphthalein. Phenolphthalein is a dye that changes color when it takes on an H+. Now it does that at about pH 8. Okay? Technically, it's usually pH 8.4. Okay? And what this does is, as we add extra sodium hydroxide, we're going to eventually run out of all the HCl, and this will no longer be going to a neutral solution. So every drop of sodium hydroxide we add past that is going to make the pH shoot up really fast. And that's going to then cause the phenolphthalein to change color. Okay?
So when it changes color, when the solution becomes more basic?
Exactly. It's when we have excess in AOH that it changes color.
That's the word.
Yep. You got it.
Solution and pink in the sodium hydroxide solution.
The reason I wanted to show you this is where a lot of students have trouble and they would go, oh, it's done. I saw pink. Okay, but that actually is not the end point, is it? Exactly.
As the sodium hydroxide solution from the burette is added to the flask, the color characteristic of that solution appears where the drop...
See how they stopped? And it actually stopped being pink completely, right? Because it got a chance to catch up.
Enter the solution in the flask. As the contents of the flask are mixed, the color disappears because the sodium hydroxide reacts with the hydrochloric acid.
Okay. Now, that is completion. They actually overshot by a couple drops. But whatever. It's kind of funny because sometimes when I get these book videos, their production values are much nicer than I can achieve because I do not have a nice camera that actually mounts them. Yeah. But their lab technique is actually kind of shit. Like, you should be doing a partial drop to get this to go. You saw there were like 3-4 drops later. Oh, or stop this. So that'd actually be kind of shit technique. And see how
as the reaction comes closer to completion, it takes longer for the color due to the added sodium hydroxide solution to disappear. The end point.
Now, this actually is why you should keep stirring. Remember, in the directions it probably said something along the lines of you should keep stirring. Yep, for another 30 seconds, right? And the reason that's happening is, so as it becomes where you have very little HCl in solution anymore, it takes a while for the NaOH to find those and actually react, okay? It's kind of like if I was asking you, okay, go ask another student, so go ask 5 other students a question. Well, you can get the first 4 pretty easy, but once you run out of students in this case, you're going to have to go search for them, right? And it's going to take you longer. And same thing here. And so we didn't actually hit the endpoint before. What happened is it looked like we had hit it because it just took a while. Okay?
So it really hasn't.
It's not done. No. Yep.
When the titration has been reached.
Again, don't do that. Yeah. What you want to do at this point is you'd want to do partial drops. So you get a drop formed, you take your water bottle, squirt it on the drop, and squirt it in there. Okay? By using your water bottle.
When the pink color remains for at least 1 minute following the addition of the last drop of the sodium hydroxide solution.
No. Once it's done to completion, it will maintain its color for an extended period of time. Now, it may actually turn clear if you left that for an hour, okay? But what happens is that the CO2 in the air actually will acidify the solution. Yeah, you would have to seal it. And, okay, so not only the acidity in the air would acidify it, but if you leave it in glass, the sodium hydroxide will actually react with glass. Yeah. So you basically just watch it for a minute or two. If it doesn't turn clear and you're stirring it that entire time, you're good. Okay. And then you just set it to the side. If it turns back clear after an hour, just ignore it. Yeah. The other thing that can happen if you're in very strong basic solutions, the phenolphthalein actually only stays pink up to about pH 10 point something. Okay. And so if you're in very strong basic solutions, you can actually digest your phenolphthalein indicator. You can destroy it. Yeah.
I didn't realize glass.
Yeah, so have you ever seen the glass where they look really, really just awful? Like not just, kind of the reverse. They look kind of wavy. Have you seen that? Where the glass starts looking wavy. Like the sidewall is clear over here, and then all of a sudden it looks like a mirage. Yeah. That's because somebody left the NaOH in it for a long time. So NaOH will actually react with and dissolve glass. Yeah. And if that baked on stuff, you can leave NaOH in there for a bit, scrub it out later, and it'll, yeah. That's how you get rid of that. Yeah. Now, normally we wouldn't want to use NaOH because it takes a while. So like when I worked with stuff that was silicon deposits, it literally would deposit silicon onto the sidewall of my glass. I would use like HF. Hydrofluoric acid will just dissolve a layer off the glass in seconds. Yeah. And see, you can just dissolve anything off your top layer of glass, and you dissolve the top layer of glass off as well. It's okay. Kind of like us. You know, we have 7 layers of dead skin. Yeah, we can, that's that skin that peels off you sometimes. That's what that is.
Well, I saw, not this is the same thing, but I saw a video last night. This woman was cooking in a big wok, and she put baking soda and lemon juice and water in it, and just ate everything off the can.
Oh, yeah.
Like, clean.
And what you're looking at is an acid-base reaction happening that creates CO2. And so it actually loosens particles while it's doing that. But you're also looking at the baking soda is a great scrubbing agent.
But she didn't even have
No, I'm saying it's an abrasive agent as well. So her stirring it and having it swirling was actually abrading the sidewalls. Yeah. So she was scrubbing it just by the stirring. The heat then was making those reactions happen really fast on the sidewalls under her stuff she was trying to rip. And it does work quite well, though it does need to have some looseness to it. Like, it doesn't work if you really bake the shit on. Yeah. And I wouldn't do that on cast iron. No. Because you're going to dissolve parts of the cast iron off, too. Yeah. But if it's between that and it's gone and dead, then it dissolves in the cast iron off. You'll have to re-prep it, though. Yeah, which is annoying. So this right here is, again, your titration. In this case, though, we're going to be using a pH meter, okay? Did I mention the limits of an indicator pH meter? Don't use them in oil. They need some ions to, Yeah, so pH meters and indicators, they do not work in things like oils. They have to actually be able to dissolve. So if you use like your pH paper on oil, it doesn't work. So, did you guys ever make soap yet? No? Okay. Come to me organic, we'll make some soap. Or I kind of do a watered down version in 100 lab now. So if you were to try to test your oil and soap, you actually have to wet the pH paper first because it doesn't work without the water. The other thing is pH meters have to transmit an electric signal through here. So a pH meter will not work if you're using ultra pure water that doesn't have any ions to conduct through, or if you're doing oil, which again is not conductive. It only works if you're using it on water that's conductive and if it's properly calibrated. Okay, so anyways, this is the pH meter right here. This is the pH electrode. You dip that in here. This is the analyte we're analyzing. We're adding titrant to it. And in this case, what you would actually see is the pH value. Now, be careful. The pH value you're going to get for your endpoint actually depends on the analyte you're analyzing. Okay? So if you were doing what we looked at before, sodium hydroxide and HCl, that would give you a pH of 7 at endpoint. Okay? On the other hand, if you're doing this for like acetic acid, you're going to end up at like pH 8 something. And that'll be your endpoint. Because your endpoint's going to be a buffer, right? Rather than a neutral solution. Okay? It's a very common mistake even graduate students make all those mistakes, by the way. Our graduate student level mistakes, I've seen like chemists make them and screw that up. I've seen people that write books make them and screw that up. So it's like, I just gave you secret sauce. I pulled back the curtain on you. So if we're going to be doing a strong acid, strong base titrations, this is going to be a strong acid with a strong base. We write that as typically HX plus MOH yields MX plus H2O. Notice that's a salt and water right there. The pH versus the volume of titrant are strong base, and we would then identify 4 regions on that plot. Region A is going to be the initial pH of your solution. It's before you add anything. And so that region, you would just to get the pH, you take the pH equals negative log of your H plus concentration, and because we're a strong acid, whatever concentration of strong acid is our H plus concentration, right? So region B is actually the segment where we have the initial pH up to the equivalence point, okay? And that's going to be where not all of our acid is neutralized yet. So our pH is actually just the remaining H plus concentration. So it's our strong acid minus whatever strong base we put in so far, okay? Remember, you gotta do those in molarities though, okay? Okay, so region C, this is the equivalence point. This is going to be where you'll have an equal amount, equal moles of acid and base. By the way, this is typically done in what's called normalities or normals, okay, which are N, capital N. And basically that says that if I have a something like a 2-hydroxide base, that's going to count for 2 of the acids on it, okay? So if I had an OH2 here, this would be a 2 equivalent. Okay, so anyways, I had strong acid, strong base together. Once it's equal amounts, equal moles, that's going to give me an equivalence point that will be exactly 7 in this case. Okay? The region D is going to be the segment that's after the equivalence point. The base is going to be continuing to be added. The pH will be determined by the concentration of your excess hydroxide. So whatever amount of hydroxide you added, subtract the strong acid from it, and that excess gives you the POH first, and then the pH. Okay? And again, that's just excess base at that point. This is actually what that looks like. You'll notice it's a straight up sigmoidal curve here. And so this is region A, this is region B, C, and this is region D. Region D can extend basically up to the concentration of your base. So the pH of your original base, it will extend up to that, but it'll never actually cross it, right? Because you can't get more basic than the original base. Okay, anybody have any questions about those? Lose anybody? Yeah. So this would actually be the molecular view of a titration of a strong acid with our strong base. So we're adding sodium hydroxide to this. It's reacting the H+. That's going to leave us with sodium chloride from the HCl, and we'll have waters that were made from the H+ and OH-, right? And so that is salt water. So let's suppose the 25 milliliters of 0.255 molarity HCl is titrated with 0.150 molarity solution of a strong base, KOH. Let's determine the pH at the following points. Okay, so what's the pH going to be before we add any KOH? So this is just going to be the concentration of the HCl, negative log of that, right? So we just take the 0.255 molarity HCl, we take the negative log of that, and that gives us our pH right there. Anybody have any questions? Fantastic. Okay, so next, after 4 milliliters of KOH solution is added. Now note that we started with 25 milliliters of this right here, didn't we? So if we add 4 milliliters of KOH here, we're still going to be mostly acid, right? Because the KOH solution has a lower molarity, in fact. So we would have to add more than 25 milliliters of KOH to fully neutralize it. Okay, so what's going to happen here is we basically just have to do a bit of stoichiometry. There are shortcuts that can be made. If you guys are still using the same lab we used to use, then you use the shortcut. Most of these labs with titrations, they give you the shortcut method because the calculations are quite easy. Okay? So after we add 4 milliliters, what we're going to do is we're going to take, this is 25 milliliters right here, in liters, right? We multiply that by molarity, which is moles over liters. That gives us moles of HCl. We do the same thing with KOH. So we had 0.004 liters. That's 40 divided by 4, divided by 1,000. And then that's times the concentration, 0.150. And that gives us our moles of KOH. We're going to take our moles of HCl minus our moles of KOH, right? Or another way of saying that, big number minus small number. Okay. And that would give us our moles remaining of our H+. So we're then going to take that number, we're going to divide it by the total volume. Now remember, the total volume is no longer 25 mils, is it? We added 4 mils to that, okay? So we're going to divide that by 29 milliliters, or another way of saying that is 0.029 liters. We get the molarity of the H plus again. That's 0.199 molarity H3O plus. We take the negative log of that, and that would give us our pH. Anybody have any questions about those? No? Okay. And the pH ends up being 0.701. Notice the pH will go up a bit. Yeah, because we added some base. What's the pH at equivalence point for a strong acid, strong base? 7, yeah. By definition, right? Yeah. Yeah. These ones, more and more definitional stuff is being added. And so if you understand the definitions, things become really easy, right? Yeah. Now, you could have actually just went, okay, at equivalence point, what is equal? Moles, right? So that means I have 0 moles of both of these. It's just the autoionization of water then, isn't it? And that means it's pH 7. Okay? That's the other way you could think of it. So, after 50 milliliters of KOH solution is added, so we're adding 50 mils now. Basically, this is the exact same problem we looked at before, but instead of ending up with HCl left over, we're going to end up with which left over? KOH, isn't it? Yeah. So we're going to take, again, the 0.05 liters of KOH, because this is now 50 milliliters of KOH instead. And this is going to be times 0.150 moles of KOH. This is going to give a value of 0.0075 moles of KOH. We're going to subtract the initial moles of HCl from the total moles of KOH. Again, big number minus small number, right? Because we're going to end up with excess of this. Okay. If you go the reverse direction, you get a negative number. Do you know what you do? You go, whoops. And then you get rid of the negative, and you write KOH instead. Okay? There you go. Okay, so we end up with 0.001125 moles of KOH. Okay, we're going to have to take that value. This is going to be divided by our total volume. So in this case, 25 milliliters plus 50 milliliters, giving us 0.075 liters. Divided by that value, that gives us 0.0150 molarity KOH. The next thing we have to do is we have the hydroxide concentration now, don't we? So we want to get into pH. That means we're going to have to take 14 minus the negative log of that value. We go ahead and do that. That gives us 12.18. Anybody have any questions about that? Okay. And notice that we have quite a bit of excess base, don't we? That makes quite a bit of sense, actually. Should be pretty high pH. So the strong base, strong acid titrations is going to be similar to a strong acid, strong base titration. It's just going to have a sigmoidal curve with that's flipped. That's it. Oh, okay. Let's go ahead and we can cover this and then we'll be done. Okay. So the region A is going to have a pH that's determined by the initial concentration of the base. The pH in region B is going to be determined by the concentration of remaining base. pH in region C is 7, equivalence point again. And the pH in region D is going to be determined by concentration of excess acid now, because that's what we're adding. And it just looks like that. See how we just flipped it? Okay, we'll start up here next time. You all have a wonderful weekend, and I will see you on the flip side of that. Okay? After you've resurrected from your rest.